Welcome to section 4.3, Useful Counting Rules. In this section, we'll learn how to count the number of possible outcomes in a variety of situations, something that becomes critical when calculating probabilities. Whether you're scheduling events, building teams, analyzing product variations, or modeling outcomes in a game or business decision, counting rules help you stay organized and precise. Imagine trying to list every possible team combination from a group of 10 people by hand. That would take forever. Counting rules let us calculate how many possibilities there are without listing them all. This is incredibly helpful when we're working with probability, where we often want to know, out of all of the ways something can happen, how many lead to a desired outcome. For example, suppose you're managing the Avengers. You have 6 members available, and you need to send 2 on a stealth mission. How many unique pairs could you send? You don't want to write out every single pair possible. Instead, we'll use counting rules to get the answer quickly and accurately. When all outcomes are equally likely, like in a fair game or a simple random draw, we calculate the probability of an event A by dividing the number of outcomes in A by the total number of outcomes. Let's say there are 10 possible snack choices in a vending machine, and 3 of them are chips. If you were randomly select one snack, the probability of getting a chip is 3 out of the 10 possible options, or 0.3. So anytime we use counting rules to find how many total and favorable outcomes there are, we're setting ourselves up to compute probability easily. Let's start with the simplest form, the basic counting rule. If you have 2 stages of a process, and each stage has a fixed number of choices, then the total number of outcomes is the product of the options at each stage. For example, imagine a fast food menu that offers 3 sandwich choices. We have chicken, beef, and veggie. And there are 2 drink options, soda and water. So I can build combos by picking 1 sandwich and 1 drink. Now I want to know how many unique combos are possible. So I could tree diagram it, do a soda and water for each choice of sandwich, then total my outcomes, right? I have a chicken with soda, a chicken with water, beef with soda, beef with water, veggie with soda, and veggie with water, for a total of 6 possible outcomes. Notice that matches 3 times 2. So I could get it a lot faster if I just multiplied. This rule extends to clothing combinations, travel routes, and app design flows, anytime choices are made in sequence. We can extend the basic rule to more than 2 stages. Just keep multiplying. Suppose Peter Parker has a busy week ahead. He has 2 days for lab work, 3 possible city patrol shifts, and 2 dinners scheduled with Aunt May. How many possible combinations of his week are there? Twelve possible ways he could arrange his week. This is especially useful in business scheduling, classroom planning, and decision tree analysis. When you want to know how many ways you can arrange all items in a group, use in factorial or in with an exclamation point. That's how we read that exclamation point, factorial. It means we multiply a whole number by every positive whole number below it. For example, 5 factorial, written as 5 exclamation point like that, equals 5 times 4 times 3 times 2 times 1. Every number down to 1. Multiply this out. 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1 is 120. It tells us how many ways we can arrange that number of items in order. Factorials grow really fast, and they're the backbone of both permutation and combination calculations. For example, if there are 5 student posters to hang up in a hallway, how many different ways can we arrange them? We know immediately it's 120, 5 factorial. That's 120 different orders for the 5 posters. This shows up in tasks like arranging displays, lining up contestants, or generating codes. You might be wondering why 0 factorial is equal to 1. At first, that seems strange. How can multiplying nothing give you 1? But mathematically, it makes sense when we think about how many ways we can arrange 0 items. There's exactly one way to do nothing. Leave the space empty. So 0 factorial is equal to 1, meaning there's one valid arrangement of 0 objects, the empty set. For example, suppose you have 0 tasks on your to-do list today. How many ways can you arrange them all? Just one, by doing nothing at all. That's your one arrangement. So 0 factorial is equal to 1. Now let's talk about permutations. These count how many ways you can arrange or choose items when order matters. The formula is n factorial over n minus r factorial. So, to use this probability formula, let's look at an example. Suppose 4 interns are presenting, and you want to select 2 of them to go on stage, one after the other. The order matters because the first speaker may get more attention. So using the formula, the probability of getting, or the number of different ways we can order the 2 speakers out of the 4 possible interns is 4 factorial, our number of interns, over 4 minus 2 factorial, or 4 factorial over 2 factorial. Well, 4 factorial is 4 times 3 times 2. So that's 24. 2 factorial is just 2 times 1, so that's 2. 24 over 2 is 12. So this means there are 12 different ways to pick and order those 2 presenters. Sometimes order doesn't matter. Only which items are selected matters. That's when we use combinations. The formula is n factorial divided by r factorial times n minus r factorial. Let's say Tony Stark wants to send a 3-person team from 5 Avengers. He only cares about who goes, not in what order. So, if we plug in here, we would have 5 factorial over 3 factorial 5 minus 3 factorial, or 5 factorial over 3 factorial 2 factorial. And by the way, I'll show you a fast way to calculate this without plugging it into a calculator. 5 factorial is 5 times 4 times 3 times 2 times 1, which is 3 factorial. And notice I have a 3 factorial here and here, they cancel. So I'm just doing 5 times 4 over 2. Or I could cancel the 2 with the 4 and leave a 2. So 10 is my final answer. So there are 10 possible 3-person teams. Combinations are great for situations like forming groups, drawing lottery numbers, or choosing members of a committee. Let's compare the two. Use a permutation when the order matters, like giving out awards for first, second, and third place. Use a combination when the order does not matter, like selecting 3 finalists to move the next round. It's like the difference between choosing a playlist where order would matter versus picking 3 songs to play on shuffle where the order doesn't matter. Think carefully about the question. Is order part of what makes the outcome unique? Let's walk through a full example. You have 6 students. First, you need to select 3 to present. The order would matter. Then select 3 to join a committee. The order doesn't matter. For the presentation team, we would do 6 and 3 as a permutation, right? So we would do 6 factorial over 6 minus 3 factorial, or 6 factorial over 3 factorial. Again, I can cancel the 3 factorial and just have 6 times 5 times 4 left. So 30 times 4 is 120. For the committee, though, right, this is a combination. I'm doing 6 choose 3. So 6 factorial over 3 factorial. And then I'd have 6 minus 3 factorial. So again, another 3 factorial. Again, the 3 factorials can cancel. And I would have 6 times 5 times 4 over 1 3 factorial. But notice 3 factorial is just 3 times 2 times 1, so 6. So I can cancel it with the 6. So 5 times 4 leaves me 20. It's the same group of students, but the structure of the selection changes the math entirely. That's why identifying whether order matters is the first step to solving these problems. To wrap up, use multiplication rules when building outcomes in stages. Use permutations when the order of selections is important. Use combination when order doesn't matter. These rules help you model real-world processes, from group planning to risk modeling to sports tournament design. Mastering when and how to use each rule gives you a powerful tool for calculating probabilities with confidence.